Straight away from looking at the diagram in this question, it looks like a classic moments question. So once again, we need to get our own good clear force diagram drawn. And in my lab, I've emphasised the beam in black because we're only drawing the forces that act on the beam. So we've got the weight force, 20G. We've got a tension force acting at the point D. That's where the string is attached. And then there's a hinge at A. And whenever you have a hinge, that means there's an unknown force that I've drawn with a squiggly arrow. But we're going to understand that force in terms of two components, which I usually label as H and V, or X and Y. Just two letters to use for those components. Okay, so there are three forces: the weight, the tension, and the hinge. But the hinge has two components. Okay, find the tension in the rope. We're going to have to take moments, and the best place to take moments about is point A, so that we lose the hinge forces completely. So we're going to take moments about A. We've got the 20G weight force. That's in the positive direction, multiplied by a distance of 1.5, because it's a uniform beam. The weight is in the middle. And the only thing going against us is a component of the tension. And like I've drawn in my diagram, is the perpendicular component of tension, perpendicular to the beam. The distance I've put in as 0.5. That comes from a little bit of trigonometry in that triangle that the string makes with the wall. Okay, so force times distance. We've got T cos 30 is the force, times its distance from A is 0.5. And these moments must make 0 because the beam's in equilibrium. So force times distance minus force times distance equals 0. And if you just simply rearrange that, you get T. You can either have an exact value of 392 root 3, but because we've used G as 9.8, we should actually give that to 2 or 3 SF. So 679 or 680 if you give 2 SF. Okay, only 4 marks, but the diagram takes a minute or two to make, but it really pays off. Okay, part B. Find the direction of the force exerted by the wall on the beam. That's asking us about this squiggly hinge force, its direction in particular. So we need to find its two components, and then we'll do some trigonometry. Usually that's with tan to find the angle that it makes. So we need to find H, and we need to find V. So 2 more equations. We can look vertically and we can look horizontally. So for part B, we're going to have a horizontal equation and we're going to have a vertical equation. And because the beam's in equilibrium, both of these equations will equal 0. So horizontally, we've got H, the component of the hinge force, to the right, minus there's a component of tension, and it's the one I've not drawn. It's T sine 30, and that's acting left. Nothing else is acting there horizontally, so this equals 0. Vertically, we've got V, and we've got that component of tension which I have drawn, T cosine 30, and we've got weight going downwards, and again, all those three together equal 0 because we're in equilibrium. So we've got 2 equations, and we already know the value of T from part A, so we can substitute all of that in, and it turns out that the H, the horizontal component, has an exact value again if you want it, 196 root 3, but as a rounded value that's 339.5, and V from my equation actually turns out to be negative. I get negative 392. So that means I've just drawn V in the wrong direction in my diagram. I've drawn it vertically upwards. That negative sign tells me actually acting vertically downwards. That's no problem at all. We'll just correct that when we find the direction. Okay, so let's scroll down a little bit. We're going to make a triangle for H and V, where we look at H going across, V is going down, and we want to find that angle theta. Hopefully you can see tan theta equals V over H. So if you use arctan, you should get a theta value of 49 or 49.1 degrees. And we should specify clearly, so that's a direction below the horizontal and away from the wall. So your full answer to B should be, let's write it on the lines, it acts at 49.1 degrees below the horizontal and away from the wall. Just a nice, careful description of the direction. It's below the horizontal, not above, even though I thought it was above in my first diagram, and it's away from the wall, not into the wall. We're being really clear there. Okay, part C. If the rope were not light, how would this affect the tension in the rope? So we need to focus there to talk about what happens to the tension in the rope. Explaining as best we can. If the rope is not light, so the rope has mass, the consequence is actually that the tension is different at different places in the rope. And higher up the rope, so the closer we are to point C in the diagram, we're going to get greater tension at point C, and it's going to decrease down the rope to point D. So overall, yeah, the tension in the rope will increase from D to C. And the reason for that is because it's supporting its own weight. Quite an unusual one there, but it's only 2 marks. And it must focus on the tension in the rope. So the tension increases from D to C. It changes along the rope because it's supporting its own weight, and the top of the rope has got the most weight to support. So that's where the tension is greatest. Okay, it's plot twist. The rope is now removed. It's replaced by a longer rope, and it's attached to the wall at C, but now it's attached to the beam at G. So we need a new diagram, which I've drawn on the side here, where we look at this new configuration. The beam remains in equilibrium. Show that the force exerted by the wall on the beam at A now acts horizontally. Okay, if I want to show that, then basically my goal is to show that V, the vertical component, is 0, so that the hinge force only has a horizontal component. And there's a neat trick to do that, which is to take moments about G this time. Okay, it's probably not the only way, but it's the most efficient way, I think. If I take moments about G, the tension force won't be there and the weight force won't be there because their lines of action both pass through G. And now we look at the components V and H of the hinge force. The component H of the hinge force, its line of action also passes through the point G. So that force won't be in our equation. So the only force in our equation is the V, the vertical one. It's an anti-clockwise moment, so technically I should have a minus sign. Minus V times 1.5. Well, those are all the forces. We've taken care of them all, and because it's in equilibrium, the sum of all those moments should equal 0. Well, therefore V does equal 0. And therefore, the force exerted by the wall on the beam now acts horizontally. Therefore, the force at the wall acts horizontally. Again, we're writing down our conclusion statement to show that we've fully answered the question. That's it.